Good afternoon. We're doing a semester of classical mechanics. This is a book that some of you have already. It's free, courtesy of the PHYS Fund for the physics department. The book that you have right now only has the first unit. The rest of the book will come as we need it. In fact, I will be giving you chapters 2 and 3 fairly shortly. When you're all done filling it, this is the size that it will assume. So you'll probably enjoy not having to carry as much. And of course it's 3 rings, so you can take out stuff you're not using and make life easier. The book is also online, and the website that gives you the lecture notes, be it our website or else the university Blackboard, which we haven't activated quite yet, so we're using the Cavern one. It's going to have about 28 lectures, and you can get an idea of what they're like by looking at 2013 thing, which is also on our website. We're busily trying to improve, particularly improving the visibility of the video YouTube entries for each of the 28. Now, the thing that we're going to do today is very important conservation of momentum axiom. And the very first lesson is if it's classical mechanics, the axioms begin with momentum most easily. The quantum mechanics, and I should mention that the real goal of this book, besides giving you some really neat insights for classical mechanics, is the connection between classical and quantum. And that's going to be shown in pretty much the last chapter of this first unit that we're doing now. That's chapter 12. But to get to that point, we're going to do some really simple stuff. We're going to just start out looking at collisions on an interstate or a freeway between an SUV, a monster car, and then a little Volkswagen. And the picture over here on the right is of those 2 vehicles will appear here shortly. And the idea is to find a really neat geometrical way to estimate or to calculate the final velocities from the initial velocities. It's a very important part of mechanics, is doing just that for complicated systems. This is perhaps the simplest system. If I make some idealizations, that has to be discussed as well. So we're going to mention how all of this is applicable to much more complicated stuff. But the 2 kinds of collisions that we'll see immediately are totally inelastic, which we name crunch, and that's probably what would happen on a real freeway, or perfectly elastic, which we'll call a kabong collision. And those are more like what you might have in a parking lot. So we'll change scale on the geometry to discuss that. But the geometry will be the same for doing either of these 2. The real world lies somewhere between those, and that's a typical thing about all of physics, but particularly classical and quantum mechanics. You make these ideal models and then hope that you encompass essential features, neglecting essentially an infinite amount of other things. Now, the geometry of the ideas behind this are really key, and we're going to be starting with the Galilean symmetry of translation. Now, at the end of this course, in Unit 8, we will find ways to understand the modern translation, which is a breakdown of Galilean to Lorentzian. We'll get to that in due time. And then I want to put this geometry in algebraic terms, and this is where our little exercise with two bodies, two cars, will give us the vector algebra for what we call a quadratic form. We're going to need a lot of those things. So this vector algebra, or really tensor algebra, because it's a quadratic object, will be the main topic of the last part of this lecture today. Now the simulations that we're going to be using for the next 2 or 3 or 4 lectures are obtained on the web, and I'll point those out in just a minute here, at least for one of them. So here's the deal. We're dealing with a problem in space and time. We're dealing with a poor little Volkswagen that's chugging along here pretty slowly, about 10 miles an hour, and a mean old SUV who is coming in at 60 miles an hour, and he's not paying attention. He's busily texting to his significant other and not paying attention to the road, and the result is, well, it could be, most likely, a crunch. Totally inelastic. That's probably the situation you would have, where they stick together.
What is on y-axis?
And the y-axis here is time here, and we're just following that in pieces right there.
But why it is decreasing? 48, 36 seconds, 20.
This is the amount of time to collision. We're counting down.
Oh, okay.
Right? Does that make sense?
Yeah. So 42 seconds for collision.
Exactly. So if I switch over to this one over here, what I'm going to do is first show probably the most realistic thing. Now the way you work this thing is you right click, and then you get a menu for a whole bunch of things. But I'm particularly interested at first in this collision. And you'll see why, that this is the one that really solves the problem, and you can get the other one sort of for free. So there is the SUV at 60 miles an hour. Oh, it's clunked the Volkswagen. Okay, and the two of them, as you can see, go off together. Now if you want to repeat the thing, this is the time equals 0 thing that starts at the end. So there they go, and this is the plot of velocity versus velocity that we'll use to solve this problem. But before I do that, probably I should go back and just show you one other scenario that's here, and that one would be this one, which shows the time. This would be the inelastic one, so that you see them in time doing the crunch. So this is essentially the picture that is shown both in the first figure of the textbook in chapter 1, in which they are stuck together. The other possibility, which we would like to have, is the most pure of solutions, a perfectly elastic case.
Dr. Harter, in this graph, first graph, what is x-axis and what is y-axis?
Well, this one is what we would call a Minkowski time plot. You probably are used to, in calculus, plotting x versus t. That's a Newtonian time plot. This has been turned on the side. And that's one of the things that's explained in quite a bit of detail in chapter 1, along with the geometry that we need for other things. But that's really what we're doing. We're imagining that time moves upward from some minus value to some positive value. If this is
on the left
origin.
graph?
And here, we're just watching the thing go in x. That's an idealization. We're not going to let the thing leave the road, so y is not necessary here. I could just take this graph away and show two cars running into each other. Okay, so that makes sense? Yeah. Okay, so the deal is, what are the usual ways of solving either one of these two problems, or the ones that live between? Conventional solution, you see, which we're going to eventually derive by doing what we're going to be doing, is, first of all, momentum conservation. That's, yes, yes sir, momentum conservation. We've got to do some justification of that, but proving momentum conservation, it's an axiom. The proof is not possible in classical framework. The proof of that comes by realizing that they're the underlying quantum waves, and that's a more fundamental description that I say will be a Unit 8 topic. But we're going to sort of nibble at it as we go along through this course. And then energy conservation. You know that the sum of the mv squared is the same before and after. Actually, it's 1/2 mv squared, and that's a little rub that we need to go together as we try to elegantly derive, basically, this one from this one. What is it that you need to say in order to get what is called kinetic energy? And it's going to come out of this. It's going to come out of this geometry that we have here. So, this unconventional way, I claim, and I think you'll agree with me after we do it, is, shall we say, quicker and slicker. You just have to draw 2 lines to solve this one. Then you have to draw a circle to solve this one. So that's a lot, I think, more streamlined than probably what you're used to. And certainly the way we're teaching UP 1 as we do here at the university. So the first thing and the key to all of this sort of geometry that we're going to be developing is to plot a velocity-velocity plot. This just doesn't seem to be part of much of our literature, but it's really powerful. It's a double speedometer. It's the Volkswagen speed versus the SUV speed. Before I go any further though, let me make sure, since we have people here who are not used to the English idiom, do you all know a VW? You don't? Okay, we're going to have to mention that that's Volkswagen, means people's wagon. Came out of Germany after the World War II.
It was Hitler who contributed. And
they're nice little cars, and they're actually still kind of nice and little, but they're, you know, a little bit more pimped out than they used to be. That's this one. Now this one right here, SUV, does that ring a bell?
Sport utility vehicle.
Sports utility vehicle, right? That's another war. This thing came out of the Iraq, or a little before the Iraq War. Okay, it's a big nasty car that gobbles up lots of gasoline and makes this nuisance of itself, is the way I'm going to say, at least for this little vignette here. So all we're going to do is we're going to say, okay, I started with 60 miles an hour and 10 miles an hour, so I'm just going to draw a point on a graph, and I would recommend that you do this just to get used to what we're going to be doing for the first part of this course. You're going to need a couple of rulers. Go ahead and pass those out. And we need some compasses. These are 3 compasses here that are pretty high quality. I'll pick one of them. There's one right there. And we'll be using that twice today. And on the board right here, I have a graph that you should probably make right away. If this is an inch on your graph paper, that would probably be a nice scale. You don't have to be too careful with this one because it's so simple and so obvious, the numbers. But basically what we're going to do is have an initial 60 miles an hour and 10 miles an hour right here. So this is going to be a point that I'm going to just be arbitrarily calling VI for initial. I'll go ahead and spell it out. So that's where the collision starts. And then the question is, what happens next? Now the thing that is mentioned in this vignette, 60 mile an hour, self-axing, 4-ton, SUV, rear ends, 10 mile per hour, 1 ton VW. Now those aren't the exact numbers. Actually, VW now is close to 2 tons. As I say, it's been gussied up. The SUVs that you could get a tax deduction from George Bush have to be 6 tons, but this is let's call this the sport, the beginner's model of the SUV. It's 4 tons. Okay, so what we've got here is a 4-to-1 ratio, and that's the key to this thing. The idea is, and this is our axiom right here being stated now, that the mass of the SUV times the velocity of the SUV plus the mass of the Volkswagen times the velocity of the Volkswagen is a big fat constant in this collision. And it's true for both of these. This is something that is good for much more than the very special case that we're going to be talking about when we do perfectly elastic. So momentum conservation is behind mechanics in a big way, and it's showing very much here. So what I need to do, starting from that initial point, is draw a line that has a slope of, well, -4 if you're looking at it as x and y versus x. So what we're going to do is, from that initial velocity point, we're going to draw a line that has a slope of -4. So basically what I'm going to do is use my graph paper, and that's what's so neat about doing geometry with a graph paper, is you can skip a lot of steps by simply counting on the graph. So I go over 1 and then go up 4. 1, 2, 3, 4. You might even put little dots there where you go. Then I do it again. I go over 1 and then up 4. 1, 2, 3, 4. And we can keep doing it. 1 and then up 1, 2, 3, 4. See, I went 1 in the negative direction, then I'm going positive in the upward direction. I go -1, +1, 2, 3, 4. And then you take your ruler and see if you made a mistake in counting. I don't think I did here, but a ruler should go through all of the points that you made on that graph. So this is just elementary graph drawing with a line that has a specific slope. That, and let's explain why that makes sense, is showing how much velocity change there will be for the VW, which is up and down, to that of the SUV, which is left and right. That is, this is the SUV's velocity scale, this is the Volkswagen's velocity scale. The idea is that for every unit of velocity that the SUV loses, the VW picks up
4 times.
4 times. For every unit, it picks up 4 times.
So 1:4, right?
4-to-1 ratio.
Okay.
Yeah.
And how do you choose the initial velocity? I mean, that dot I didn't understand.
This particular scale is just chosen to encompass the initial conditions that we're claiming here, 10 and 60. Okay,
60,
I went ahead and finished it with 100 because we're going to do some other things with it. But right now, we're really only going to be in the neighborhood of that line.
And how do you get that slope as -4?
Well, basically, algebraically, the answer is I take this equation and change it into MSUV, PSUV equal minus MVW, PVW, right? Then I divide the masses. So I get a thing that looks like that. There's delta velocity of the VW over the delta of the SUV is equal to SUV over minus. That's coming right from that equation, right? But better way to think about it, it's proportional. just as I was saying, for every unit lost by SUV, coming in at 60, right? Poor VW gets 4 times that. Okay, you've got to imagine you're the VW. Okay, does it make sense?
Yeah.
All right. So that's an axiom. This is axiom 1 for this class. We're going to try to derive everything else from that, basically, and a couple of other little things that we'll stick in that are necessary to make things work. Okay? So, we're going to look at the totally inelastic collision. Okay? It's right there, but what's there? Now remember what happened in the collision over here. They went off stuck to each other, right? So what we need is a red line, and you don't have to use red, but I will just so I can talk about it. At 45 degrees, the y equal x line, that is v SUV equal v VW line. Okay, this line right here. And we know these guys have the same velocity after they're stuck together, right? So there's the answer.
So why 45 degrees?
First look at this one, that's the easy one. There they are, stuck together, right?
Yeah.
Same velocities.
Yes.
So we've got to find the point
Okay.
on the momentum line where the velocities are equal. Simple, eh? Okay, that's the trick. Okay, first trick, trick 1, all right? Okay? Now, once you've got that, call it what you want, final crunch. I'm going to be actually giving it a different name. COM, center momentum, is what it's going to really be called. But let's just use the cartoon nomenclature that we started with. Okay? That's the answer of the first problem. The other extreme is the kabong. And where is that going to be? Well, it turns out it has to be where this circle intersects momentum line. It has to be somewhere on the momentum line. But if you take your compass and go ahead and draw a circle through the crunch point, you should get the answer to within a few percent, depending on how carefully you drew but anyway, that's kabong right there. Final kabong. And we have to see what it is that makes that the case. Now what I'm showing is approximately, my line is a little bit below the 90, but we've got a VW after the collision, if this is a kabong, going 90. That's, I don't think, survivable. But this is all sort of imaginary, fortunately. Okay.
Yeah,
And
the
the
SUV
SUV.
off the road too.
Yeah.
I mean, 90 into a ditch on the side
Yeah.
of the road is a
Well,
different thing.
We'll talk about idealization or non-idealization in just a minute. But we can also see that the SUV is slowed down from 60, just 20 miles an hour to 40. Okay? So we started with 10, comma, we started with 60, comma 10. I'm going to use the standard XY coordinate notation. And we're ending here with an SUV of 40 and a Volkswagen of 90. Okay? Good.
So,
All right, now what's hiding behind a solution like it? What is it that really makes this work? What is it that we're saying about this object when this occurs? And just for the heck of it, I'll go ahead and show on this graph here what it is we mean by that graph. And this is important. A lot of people misinterpret this a little bit. So first the thing I'm going to do is go ahead and show the glorious one, which is this second to last one, collide elastically with the dual plot. The dual plot now will have the velocity on it, okay? I could start with the crunch. I might as well do that. We've already seen it a little bit. There it goes. Boom. Now, one of the things this shows is the motion on this little line here is very fast. Okay. Now, this is an actual simulation of all the forces of Newton's and Lagrange's equations and stuff that we're going to learn programmed. But we're just using it as a tool to understand our little geometrical trick. Now, one of the things I think you might have noticed if you were watching that carefully, let's do it again because it is kind of cool, and that is that the, I'll start it over again here. Watch the red ball a little bit. Did you see that thing go up and then sort of sink down a little bit?
yeah.
Okay?
Yeah.
We'll talk about that later on. Don't pay too much attention to it right at the moment. Right? Now the next...
So you are saying that it's not exactly at 50, but
well,
it's like,
what happens is it has a lot of friction in there, and it just manages to spring a little bit. But the friction just damps to keep it as one piece of mass. So now we have a 5-ton piece of mass, okay, made of two vehicles, one and one of 4. This one right here, as you can see, is more spectacular. Boom,
yeah.
right up to 90. Okay, so that's what the simulation is giving you. That indeed is very close to what we're getting here. In fact, should be, if you did your thing right, getting exactly 90. The simulation, it can be a little bit different. We'll talk about those details later on as well. Okay, so that's the thing that we are going to be using, is the geometry that comes by taking advantage of this little pair of tricks. Now, before we go on, let's comment on idealization. First of all, if we're going to have a kabong collision, a totally elastic collision, that's probably going to have now parking a lot of it's actually these vehicles. To get that perfect rebound, you might say, without damaging appreciably either of the two vehicles, that's what an elastic really means, is that it comes out of the collision unscathed, so to speak. Okay. Now, the simulations that we're going to be looking at on the next lecture involve superballs doing all kinds of weird things, and this is a particular case of a 4-to-1 collision that we'll see in the next lecture. But what I'd like to do now is just point out, first of all, the crunch, 50-50 goes to 60, 60-10 goes to 50-50. That's what you have, is both of those vehicles now one piece of matter going 50 miles an hour. Whereas this one, okay, I think you've noticed there's something different here, but the geometry is the same. I just changed the scale. I changed the scale here, instead of to 50 miles per hour, I changed it to 50 feet per minute. That's about this fast. Okay? It's just a really careful person backing up with a modern car where you can't see the back and hoping he doesn't hear a bump. But he's going slow so that no damage, right? So using that as a scale, in a parking lot, assuming no other situations and things like that, all in a line. It's idealization. Then you go from 60-10 to 40-90. Okay, but we're doing reasonable units here. These are unreasonable units for getting a result like that. Just to, bring this thing at a little bit of reality to a terrible collision speed that would have been deadly. Instead, we don't even have to go call the insurance company. Okay, now, idealization. First of all, no background, no rolling friction, air resistance, blah, 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 blah. Make each one-dimensional. Cars are, and we'll talk about constraints, that'll be a big part of mechanics. You're constrained to ride on a frictionless rail, or on, this could be air cars on an air bench, but air has friction too. What we really like to have is cars on superconducting maglev. Very little resistance for that. Perhaps we are going to be able to build some of those things before this course is over, and do some experiments that are really quite cute that we're going to be talking about only theoretically in the next 2 or 3 chapters. In any case, the idea is that in this course, and this is starting with units 1 and 2, we're going to have a lot more degrees of freedom than 2. Here, each body actually has 3 translational degrees of freedom, so that's 6 degrees of freedom. For just translation, forget rotation, that would be a big problem that we'll be tackling various pieces of, but it's not possible to do quite the simple geometry that we just did. We can get some of it, but not all of it. And then they actually could rotate. You see, in most collisions, if you see the latest insurance ad or the latest ads to not text, resolve and the car is rolling over. So there's an extra 6 degrees of freedom for that. So if these were rigid or semi-rigid cars, 12 degrees of freedom are needed to really do a collision between these 2 vehicles. We'll be taking up a lot of that starting with units 3, particularly in unit 7. Rotations is unit 6 as well. And then, actually, we're going to be talking about molecules colliding with each other. Something like this, you see, well, it's got some vibrational degrees of freedom. We're going to introduce a little bit of that. And this is in units 3 through the end, that you would be talking about how that gets into the act. So you see, we have a whole course cut out here. We're not done just because we can draw a couple of lines and find the points. I want to make that clear before we go too further. Okay, so back to the imaginary land. What I would like to do is talk about this in terms of symmetry. Naturally, I do that because that's my field of quantum mechanics. It's also in classical. And the symmetry transformation we're talking about is Galileo's. And Galileo has conceived of, as he lived near a seaport and saw the beautiful sailing vessels coming in with their sails drawn and just coasting up to the various wharfs or docks, he conceived of the idea that if you were on board one of those things and it was moving at some speed, say 5 miles per hour, okay, then the person that was on that boat would see the rest of the world to be 5 miles per hour slower. Here I'm talking about 50 miles an hour at this point for both of these vehicles. At the moment they're stuck together. And I'm saying if I could get onto a car, I imagine in the textbook an actual motorcycle cop going 50 miles an hour alongside this, in that frame, they're not moving at all, you see. I have, by subtracting the velocity from both of them, and I have to do that if it's me doing the motion, I have to subtract it from both of them. That means I have to come down the 45 degree y equal x line to the origin here. Okay, if this is minus miles per hour and that's plus in the frame of this thing we call the center of momentum. You're going to see this COM all over the place as we discuss this. But that's the whole idea, this really magical thing that is, if I am frustrated with you because you're not doing what you should be, you're not active or something like that, say I was a gym coach or something and you're just sleeping there, I can make you all move by walking this way 3 miles an hour and you'll be going that way 3 miles, all of you, right, in my frame. There's something magical to that. That's not trivial. Okay? It seems, after you think about it, quite obvious. So obvious that you are going to be surprised, if you haven't seen relativity yet, that it's a little bit wrong. And with respect to light, it's totally wrong. A light beam comes through this room, if I have ability to look at its speed in my 3 mile per hour thing, or my 300 mile per hour, it doesn't matter, it's always going to be the same velocity. That would have made Galileo actually sick to his stomach, I'm sure. The idea that there was something in the universe that behaved like that. And then as a consequence of understanding that, everything behaves a little bit like that when they get going really fast. So this symmetry idea is not trivial when it's generalized certainly to relativity, but it's not trivial here either. Here are a whole bunch of possible frames. This is a frame where the initial Volkswagen is sitting still. I came down 10 miles an hour, okay, to be in it. All right? From so I'm talking about 50 miles an hour here. There's the VW is 0, okay? The SUV is now only 50 miles an hour, took 10 off, okay? Then I come down a little bit further here, I've got a frame in which the final sort of resting place of the SUV has no velocity in this axis, and so forth. I'm just mentioning here 5 or 6 possible reference frames of an infinite number of frames that are possible for viewing just this one collision. Now, the idea of time reversal symmetry is really key to the discussion that we're going to have here. Time reversal symmetry, meaning flip t to minus t. Run the movie backwards. Run the clock backwards. At this point, it might be worthwhile to see something in here that's time reversed. We have a clock over there, and it's getting into the lecture, so it's time to start looking at the clock. Let's look at these 2 clocks right there. Now, I just noticed that one of them has frozen a little bit.
Symmetry is problem.
This one over here should be, I don't know what happened to its poor little hand. It didn't keep time very well, but it is supposed to be about over here. I think that's about right.
No,
Is that right?
no. We started at 3:30.
Oh, there you go. It should be at 4, and it should be about there, right? Yeah. So there's correct time. This one should be up here. I have no face on it, so I can make it. Okay, I'll poof this up completely. I have to buy better clocks, but there we go. We're talking about right about there. So these 2 clocks, one going forward and one going backward, should be mirror images of each other, which is a little piece of geometry that we'll run into later on. Okay, so the idea of this is that this very special thing that we had here, flipping time, that means you flip the velocity, okay? The center of momentum, right there, this one, of all the possible reference frames, that one's really special. That there is just one velocity frame in which the time reversal collision looks just like the original. So in that frame, these two come together, and if it's elastic, spring apart. That looks the same going forwards or backwards. That's the symmetry point of the symmetry. Just, kind of neat. This is sort of thinking that we're going to need later on. But right now, it's the geometry and algebra of this that I really want you to see. This is what's going to introduce us to the geometry of Lagrange and Hamiltonian, the Hamiltonian and Lagrangian. So let's do the algebra. That's very standard. The axiom that we have, conservation of momentum, that means conservation of anything on this line. Anything on this line has the same value as this. It has the same value as the total mass of these two guys stuck together at this point. That would be the situation that would last for a long time in the crunch collision. Only briefly would it last in the kabong collision, because it would go through that point very fast, as we showed in the animation over there, and end up here. In any case, where it started, where it was along that quick path up to here or just to here, every one of those points, including those outside, have this value. This is a constant. That's what the axiom is saying for our physics, and this is the geometry of it. So we have a vector here describing your initial velocity as an x component, y component. We have a vector describing the crunch point, or the velocity at COM, and then we have later on, after going through a whole bunch of points very quickly, in the elastic collision, a final velocity up there. But they're all on this line, and they all have the same numerical value of this. That's really worth noting, really worth thinking about, that that's going to be true. And it's true in all sorts of situations, in which even ones which you land outside. I'm going to ask you how you do that later on. Okay, so we're going to define these points as final center of mass and initial velocity of SUV and VW as components 1 and 2, if you were going to count like people count vectors. Say x and y, if you want to call that x and that y. Okay? And the idea is that every point between these and those lies on this momentum conservation line. Okay? So what can we make out of that? Well, one of the things that's kind of neat is a mass-weighted average velocity at any time in these collisions is the center of momentum velocity. Remember, it's 50 miles an hour. It's the same for both, because they're stuck together right here in space. They're together in velocity space as well. Okay? So this constant, this is another wow, this is a weighted average of the velocity of the SUV and the VW, weighted by their weights. It's a good name. That's a statistical name, actually, but it's physics too. And then the total mass of 5 tons is in the denominator. Okay? So we've taken this MV and divided the M's out. That's another way to state the axiom in sort of a algebraic, quasi-geometric way. So what we ended with, 49, is what we started with, 60-10. Okay? At COM, we're at 50 times 1, 1. That's this point. Okay? And that vector I want to define as a funny unit vector. Now, a unit vector, as you already know, is a normalization of square root of 2. I don't want that. I want just 1, 1. Okay? This U is going to be that thing. That's one little algebraic trick that we need to make the tensor description of this whole collision. Okay, so let's begin that. That's the hard part of this lecture. If you are not familiar with matrices and tensors, you should be. If you're not, we've got ways to help that. So talking about this momentum conservation line, and we're talking about a vector right here along the 45-degree line. That's a vector that is some number, 50 in this case, times that vector u there, the funny unit. Okay, I'm going to go ahead and draw an engineer symbol. Now, I'm also going to define mass matrix operator so that I can describe momentum. Momentum will be used letter P, either uppercase or lowercase, throughout this course and most other courses. The mass matrix here, m SUV times v SUV, gives you that. That will be the momentum of SUV, and then VW, you see, has a similar expression in notation. All right? Does that make pretty good sense? Okay. But you see, what's really weird here is we're dealing with a vector that's not space dimension, it's different vehicles. SUV versus VW. And if we had three particles, we'd have a three-dimensional space, and so forth. Okay? That's something you got to get used to. It's a little bit of an abstraction from what you're used to if you've been taking courses in vector analysis and things like that. We're using it in a funny way. Okay? So the idea is this whole sum of components is constant. That's this thing right here, the momentum thing, that's a constant that can be written this way. There's the u, okay, u dot that p is going to be the sum of these two SUV and VW momentum. There they are, okay, there's their old definition, but that's coming from this tensor expression. You see, this is our first sort of quadratic form.
It should be u dagger, right?
Say again.
It should be u transpose, right?
Right here. Yes, u dot p, and then p, that thing is this. You see?
No, I'm saying that it should be u transpose, right? Because
U.
transpose.
Oh, you mean transpose?
Yeah.
Oh.
It should be.
You are right. You are right. A little arrow should be on top of these guys going this way, and a little arrow going this way. I leave that off for now.
Okay.
Okay, so we'll let be understood. And certainly, what you're talking about is the duality that comes with any sort of operator business. This is kind of like the ket,
Yeah.
and this is kind of like the bra in quantum mechanics. You see, that's a quadratic form that you guys are going to have to really work with day and night. Ours will not be quite as bothersome. Mostly they're real. That's one thing. Anyway, I've indicated this thing with a big engineer symbol, and this constant in a funny kind of way. Now, this vector VCOM, that's the whole vector, being the VCOM times that funny unit, that gives us an equation for, first of all, our m dot v here, see, because the VCOM and u, there's the u right there. All I have to do is multiply this thing by VCOM. And so I'm going to be getting the actual velocity of the center dotted. And again, as you say, that's a transpose vector.
Yeah.
So we should have a little arrow going this way. Then here's that matrix, the mass matrix, okay? And then here's the input velocity, okay? And what we claim from our original stuff here is it doesn't matter whether I use input or finish or anything in between. But let's just take these two extreme cases, okay? So that's what this axiom of momentum conservation is boiling down to here, you see. And this is a quadratic form that will eventually derive us an expression, a quadratic expression for energy. So what you're seeing then is this relation right here is equal to this VCOM vector. That's the thing with the transpose, and then the matrix, and then the vector Vn in its normal display there. And then here is VCOM. You see, VCOM is half the sum of these two vectors. It's a parallelogram. This has got to be halfway. This is what I call the time symmetry axis. If the VCOM here is splitting equally final and initial, then I could play the movie backwards on a collision like that, and it would be a real physical effect that could happen. But if this thing is anything less than, particularly if it gets stuck here as in a crunch, playing the movie backwards looks really weird. You get crunch, right? And then you play the movie backwards and it goes uncrunch, right? Very improbable, as they would say in statistical mechanics, and really mean it. Okay? So, this is our time symmetry axiom in physical form. Now, the other thing to notice here is that this is a symmetric matrix. That is, this is equal to that, trivially so. There is nothing but zero there. But what we're developing here is going to be valid for all kinds of weird mechanics where this is not a diagonal matrix. Effective masses are all over the place. They're due to waves. Waves can do practically anything. So you have to get used to m's that are not diagonal. And in weird coordinate systems also, they're not going to be diagonal. So what we're going to be finding is that this quadratic form involving VCOM, and that's where I can go ahead and replace this equation right here. I can replace the VCOM by the half sum and get an equation that looks like this. And the thing that will be true is it won't make any difference because of that symmetry, and I'll go ahead and point that out in the thing. The important thing is that the transpose is there. So either way you do this thing right here, Vn, let's see, no, this thing right here, fin m dot n has got to be equal to n m dot fin. So once you have that little item, then you can replace these things so that you get an equation that looks like what we're going to be seeing here very shortly. We're going to be seeing this expression right here. The quadratic form involving Vn has got to be equal to this quadratic form. And all I did was subtract a half of one of these cross terms. It can be fin in or it can be in fin. It won't make any difference because of the symmetry. So we need that symmetry. That symmetry is really important in the matrix when we do exotic mass inertial things later on. Anyway, you should recognize this one where it's nice and diagonal, SUV and VW, on the mass matrix as an equation for an ellipse. And that's telling us that whether you use the initial or the final or anything that's on an ellipse, that's this thing right here, it's as good a conservation curve or line as this one. But we had to have time symmetry in order to get that. So this is, I think, really important key part of mechanics is to realize the conservation of momentum is a key axiom, and with time reversal leading to conservation of energy theorem. You don't have to have energy axiom. It's a result. Doesn't sound like much, but you know, we're trying to use Occam's razor here. We're trying to say the least, get the most.
So you are saying that conservation of energy is an outcome of conservation of momentum.
Right. Provided T symmetry. Provided. If you don't go the whole way, if you go 3/4 or a half, sorry, energy not conserved. Now, what does happen to the energy? And that's what's cool, and that's what I'm going to give you a couple of problems to work out, and you ought to do them as quickly as you can so that you see this. This is a summary with T-symmetry. We've got to have that in there. Gives kinetic energy conservation theorem, and that's the definition of this
Elastic.
quantity here. Okay, it's the total kinetic energy. All right? So this is the one slide that sums all this up, and it's similar to one in the textbook itself.
So, to draw the ellipse, what we need to take actually, about what point we need to draw?
What I was saying here was that if in your collision you stop here,
Okay.
you're not on the ellipse anymore.
Right.
You've lost energy. You're inside, right?
Mhm.
But if you can bounce back,
Yeah.
then the conservation law is applied. Now, I think you're beginning to get a feeling for how geometry is powerful. It's letting you visualize that statement I just made. But it's also coming with some tensor stuff that we're going to need to make the class work.
The geometric construction will be later in the class. Hope that will nail that down.
There's a really neat geometry just associated with this thing. You see, this collision could start anywhere and go at that slope. That's kind of neat. If you ask a geometry teacher, hey, if I draw these all these lines that have the same slope, that's the square root of your coefficient of your major and minor axis, it's always bisected. That's kind of neat. You see, it's a physical derivation of that, sort of. You see, because physics and geometry are all a little bit mixed up here. Now, as I say, that's the important thing, if and only if there is T-symmetry. So, let's look at what would happen if I stopped right there. Okay, this is what I'm going to be giving you as a problem to work, but let's just work one real quickly here. It's for the situation we have with 4 to 1 and starting out at 60 miles an hour at 10. If I were to stop right there, okay, if I were to stop right there, I'd be on an ellipse, and it's an elastic kinetic energy. In other words, this is the most energy I can lose, is whatever it takes to get down to that ellipse right there in this collision. I can't lose anymore, because now they're just stuck, right? And all the heat is taking everything away. Okay? But now we could also look at this thing in the center of momentum. You see, that's interesting. There's an ellipse for that. And it's the smallest possible ellipse that you get as you translate two different reference frames. Another powerful thing about the geometry is all of that sort of combinatorics, or whatever you want to call it, algebra really, is very clearly displayed. So, as I say, this is a usual situation in physics. Opposite extremes. Here's our beautiful T-symmetry is best here. Most T-symmetry, okay? Where I went from this initial point all the way up to this one. Made it to the same ellipse. Okay? Started with that much energy, ended with that much energy. Okay? But in going up, I squished something and maybe damaged it a little bit, so I didn't quite make it back. That's the usual generic, real-world, dirty, frictional sort of mechanics that most classical mechanics avoid like the plague. You see, this is engineering now, you see, and you need a computer in order to really figure out what that was lost most of the time. So I just call this Coulomb. Okay, this is the general Coulomb that's in between the kabong and the crunch, where you end up right there. That's the least T symmetry. This is somewhere in between these two, most and least symmetry. You see, the real world is a continuum, depending on the mechanics of the bumpers or whatever of these colliding bodies. Okay, numerical details. We have enough time, I think, to do this. Are there any questions, though, before we leave the geometrical description and just go ahead and do the algebra? Does it make sense? I mean, this really tells the story. And there's more to it if I change a reference frames.
What is IE?
What is,
IE?
I guess I don't know.
VCOM is equal to square root of 2IE dot.
Oh, okay. Inelastic energy,
Okay.
okay? This is the E of the Coulomb, okay? This is E where we maintain our elastic kinetic just from start to finish.
So the minor axis is determined by the energy, right?
Well, the minor axis is determined by whatever, remember, we're in this space here, whatever the SUV is doing, right? And the major axis belongs to the VW. And that makes sense because the VW mass is lowest.
Mm-hmm.
And an ellipse, that is in the denominator, you see.
Yeah.
Okay?
Mm-hmm.
So it gets very big in this direction. That probably the best way to say it. Let's go back, make sure that that's clear, because when we write this equation right there,
Mm-hmm.
we can do this, right?
Yeah.
I can take this KE, you see, put it in the denominator there, and then I can make a equation for A that's the square root of these things. So that's the key numbering for the geometry. That thank you for the question. That makes sense. Yeah. Okay. I think that's fairly well documented, and you'll see it again in the thing. So there's the A right there. There's the B right there. For inelastic, okay? And for here, it's larger, you see. Both A and B are larger by the same fraction. Okay, the ellipses are congruent. Okay, let's see it in algebraic form. Once again, momentum axiom, this time with the generalized mass, some sort of weird effective mass. Or some mass tensor if you're doing rotations. We won't do that for a while, but that's, you know, we're going to be doing equations that are general for every possible thing you can think of in classical mechanics. And starting with mass matrices that are not diagonal.
But can we go to a frame where we can diagonalize?
Absolutely, if time reversal symmetry is good. Yeah, there are situations where matrix, we'll discuss this a lot when we do the matrix diagonalization stuff. We have really good ways of handling that, good ways of finding when it's possible, when it's not. You can't diagonalize every matrix. But if you put a random matrix down, the probability that it's not diagonalizable is negligibly zero. That's an interesting thing that Wigner first thought of, I think. First physicist to think of. I think mathematicians kind of knew it. Anyway, with this diagonal, okay, where V1 COM is equal to V2 COM, it is VCOM. Remember, this is number one particle, that's number two particle, okay? They both have the same component on this line and at this point in particular, okay? So putting that in for this P total, you get all of these things to be equal to just the total mass times the center momentum velocity. And then we turn those into tensor equations. Okay? So that's the thing. I multiply VCOM by that equation and end up with a quadratic form in velocities. Okay? So we have VCOM here with an N, we have VCOM here with a fin, then we have VCOM, VCOM in the mass matrix. Okay? Being this thing. So this is VCOM squared M total. Okay? So these tensor quadratic forms become very nice numerical ways to handle problems like this. Good bookkeeping is what this comes out to be. So here's our old 4:1 mass ratio of VW to SUV. SUV is the first coordinate, VW the second coordinate, maintaining all of that. Okay?
The 4 corresponds to SUV, right?
The 4 comes, the SUV's 4 tons. The VW is 1 ton. You know, we took thing. Still not up to George W. Bush, but getting there. Okay, so here I just go ahead and multiply, 60 times 4 plus 1, I get 125. The idea is that when I multiply this all out here and here, I should be getting the same thing, namely 50 times 250. So there's your the mass, let's see if I'm saying VCOM 50 coming out twice. It's quadratic form, M total. M total being 5, 4 plus 1 gives you that largest number. Now, the idea is that this P total 250 is the same at any point on that line, particularly these 3 points. And we're using T symmetry, so we can replace the VCOM by the half sum. Okay? And that is the thing that finally gives us something that is related to the kinetic energy. So we've got to subtract this oddball here, V fin M V N, and other way around, but it's equal to that. So I'm subtracting that to get me a complete quadratic form for the input, a complete quadratic form for the final. Okay, and this is another way to write it. All of these are useful relations. Okay, the transpose symmetry has to be there. It's trivially here for this one. So either one of these should give the same number. That's just a check on that. Now, the actual energies come. This is the, remember the transpose symmetry at work. With the off-diagonal gone, as is the situation with our highway experiment here, the elastic is the same at the end and the fin. Okay, so this thing right here at the inputs, remember 10 Volkswagen 60 mile an hour SUV, 4:1. Okay, this is the final. Okay, they better be the same, they say. And indeed they are. Now this is kind of interesting. This 12.5 minus that thing is giving the total as well. That's kind of useful for some stuff that will come up later on. But it's worth looking at this. Kinetic energy and the inelastic, this is reduced by 1,000. When we take that, let's see if what I'm actually saying here, in the figure that shows those two ellipses, it is giving us the difference in inelastic crunch energy for these cases. Now, this is kind of interesting. The difference between the inelastic and the elastic, this 1,000, is given by just a quarter of that cross term, quadratic cross term. Just a quarter of that subtracted gives you the difference between these two. Now this is something that's invariant. The difference between elastic and inelastic, you should get the same answer no matter where you start with a collision. So we come back and imagine all of the possible things here. Each of them would have an ellipse differing by 1,000, you see. This one differs by, these two by 1,000, by 1,000, by 1,000, all the way down to this one right here, where you're in the center of momentum frame. So I point that out just to give you a feeling for what the tensor algebra does for you. So here are pictures, movies, in all the different frames that we were mentioning, and then a couple more that are represented by parallel lines translated in the 45-degree direction. The Galilean symmetry operation giving us all of the different views, in this case 4 different views, of the same collision. Okay, whether it's elastic or inelastic. Now, what I'd like to do is take you just very briefly through the textbook where this is discussed. And I want to point out the usual way in which kinetic energy would be derived is like this. That is right about there. Basically what you do is you take the total momentum equation right here, which we've been working with just in before we did the tensor stuff, and isolate the SUV terms and VW terms to get a zero-sum relationship for the change in velocity of SUV and VW. Now, the thing, this is another way to write with the SUV things on one side and the VW things on the other. And what you do, and I need to be careful here so I don't jump too far on this, just go up a little bit here, and what is page 45 of the textbook. I point out that if you follow the usual procedure you see in elementary physics books, you can take that one and multiply it by that one, and you get a conservation of this. So this is sort of an unmotivated step, but okay, they're equal, why can't you multiply? Go ahead, multiply them, and then separate them out. And there you have, after you again put the SUV and the VW together in the final state, and the VW and the SUV in the initial state, a expression for kinetic energy. But there's a problem. It doesn't really tell you that that particular curve that you get that goes through in the geometry is this, you see. I can multiply this equation by 17 and it's still correct. It's telling you that the sum of mass and velocity squared is a conserved quantity. It's not telling you that there's something significant about 1/2 the sum of the mass and the velocity squared. The tensor thing gives you that, because it's actually nailing which ellipse are you on. So I wanted you to see that, just to see an example of the difference in logic that comes about when we are playing with these things. Now you can come, as I say here, conservation holds for any overall factor. 1/2 really is fortuitous in that derivation. But we'll see later, kinetic energy is defined as an integral of velocity with respect to momentum. That comes out to be that. You do need the 1/2 there, and then, so that makes it reasonable that this would come out and be the thing that we're interested in, namely the thing is conserved on that particular ellipse as opposed to any other. This is a very subtle point, but I think it's worth noting, simply because we then go ahead and do in the textbook, and I want you to go ahead and read this over again while it's still a little bit fresh in your mind, a linear and logical description. Jumping around when I use the slides here. If you go through this, it should become pretty clear about these three cases: high symmetry, highest symmetry, something in between, and lowest symmetry there. And there's something else that's going on here too. Now here's the tensors coming to work and doing all of that. That's the geometry that's behind these relations. And here's another numerical case that gives that weird difference between elastic and inelastic, which is a pretty useful thing to happen. Now, at the end of this, I would point out, first of all, there's the usual formulas and things that you should get used to before we go too far into this book, just tabulating them. We'll do that plenty later on. But there is something back on page 43 that I wanted to show you. Here's the thing we were looking at in the lecture. This is so that you don't call the center of momentum the center of gravity, even though in special cases you could say it was. I'm going to go get that out here if I can. I think it's in close to the end of this discussion here. Let's hope it is. Yes, this is what I'm after. This little figure here is kind of neat in the sense it's just recouping what we started with, showing the geometry of an initial point, a Carunge point, a Kabong point, so inelastic, elastic, it's all there. It's slightly different sketching of the geometry. There are the two possibilities. But when these two cars are coming together, and if you could somehow make a scale right at the center of gravity, now that's in space, you see, that's over here. That's in this drawing here. The center of momentum that involves velocity is in this plot. But you could imagine a scale containing those two cars coming together, and you're holding it at the center of gravity. That would be the location of the center of momentum that we're talking about over here. Again, a little bit of a subtle point, but worth noting. That's the kind of balance we're used to in statics, right? Here it's going on in dynamics, you see, in a velocity space. Okay, so this COM here, really crucial. Okay, I'm making the engineer's symbol once again to emphasize how important this one is. Now this is going to be important however many degrees of freedom we get or do. So this is the start of geometrical constructions that do some fairly complicated things partially. But the more degrees of freedom you have, the more screwed you get. Simply because you're always going to have momentum and energy, and you're lucky if you can get maybe one or two others in very special potentials. But most of the time you just have those two. And then a whole lot of degrees of freedom. So you get to take out 2 degrees of your freedom. If you had 100 and you're down to 98, see? Or something like that, depending on how many momenta you have. Okay? So I think at this point we're right on time to wind up. Are there any questions that well, make sure you have a problem set.